This lecture, we will see some introduction about Pesel orthogonal, Pesel unitary, and Gell-Mann matrices, and also we will see about the Casimir operators. First, we will see the properties of orthogonal matrix. It is written as O n, where n represents the n by n matrix. By definition, the orthogonal matrix is A transpose is equal to A inverse. That is, if you transpose the row and column, which is equal to inverse of that matrix, which implies A into A transpose is equal to 1, where 1 is the unit matrix. The orthogonal matrix properties are all the orthogonal matrices are square matrices, but not all square matrices are orthogonal. Orthogonal matrix has all real element in it. So all elements are real in orthogonal matrix. Uh, all identity matrices are orthogonal matrix. Uh, so we can infer from the second definition, second property. The product of two orthogonal matrices is also an orthogonal matrix. The determinant of orthogonal matrix has a value plus or minus 1. It is a symmetry in nature. Uh, Plus 1 means is rotational, minus 1 is a reflection. Now we will see about the properties of Bessel orthogonal matrix, which is written as SON. As usual, n represents n by n matrix. Definition is the same as that of the orthogonal matrices. It is actually the subgroup of orthogonal matrices. Unlike orthogonal matrices, in which the determinant is plus or minus 1, in this case, special orthogonal matrices, the determinant of a special orthogonal matrix has a value of plus 1. So that is the only major difference between orthogonal matrix and special orthogonal matrix. As a linear transformation, every special orthogonal matrix acts as a rotational matrix. Before going into the details of the unitary matrices and Bessel unitary matrices, we will see some important properties of Hermitian matrices. By definition, Hermitian matrix H is equal to H tag. That is a conjugate transpose. The properties of Hermitian matrix are the Hermitian matrix is equal to its conjugate transpose by definition. The Hermitian matrices has complex numbers, whereas just now we have seen the orthogonal matrix and Bessel orthogonal matrix, in which all elements are entries are real number. However, here is a complex number because we are dealing with quantum mechanics. However, it is diagonal entries are real because these diagonal entries uh, must be real because that is uh, that shows the eigenvalues because the eigenvalues of Hermitian matrices are always real. Hence, the diagonal entries are real. The determinant of Hermitian matrix is real. The inverse of the Hermitian matrix is a Hermitian as well. Uh, Similarly, the conjugate of Hermitian matrix is also a Hermitian matrix. Now we will see about the properties of unitary matrices as well as Bessel unitary matrices. By definition, unitary matrix is U star is equal to U inverse. That is it. If we take the complex of the matrix it gives you the inverse of the matrix, uh, which leads to u star is equal to 1. This is a unit matrix. The properties of unitary matrices are all unitary matrices are a square matrix, but not all square matrices are unitary. The unitary matrix has complex element in it. So unlike orthogonal matrix, it also has a complex element like Hermitian matrix. That's why I have given some important point about the Hermitian matrices. All identity matrices are unitary matrices. All identity matrices are unitary matrices. Unitary matrices together with the matrix product operation forms a group called the unitary group. The product of two unitary matrices also a unitary matrices. All unitary matrices are diagonalizable. So that is very important. And modulus determinant of unitary matrix is equal to 1. Remember that in the case of orthogonal matrix, the determinant is plus or minus 1. And in the case of special orthogonal matrix, it is plus 1. Here, the modulus determinant of unitary matrix is equal to 1 because it has a complex entry. And the special unitary matrix, which is represented as SUN. As usual, SUN represent n by n matrix. Here, for unitary matrix, we are writing as UN. So n represents the n by n matrix. The major difference between the Bessel unitary matrix and the Bessel unitary matrix is it has all the properties of unitary matrices except instead of modulus determinant of U unitary matrix is equal to 1. Here, determinant itself is equal to 1, not the modulus. That is the major difference between the unitary matrix and the Bessel unitary matrix. So now we will see some of the most important properties of unitary matrices and Bessel unitary matrices. A unitary quadratic matrix U with n rows and n columns can be written as U is equal to e power I h, where h is the Hermitian matrix. These matrices forms a group under matrix multiplication. So if you multiply two unitary matrix, that gives you another unitary matrix. This group we can call UN. It is represented as UN as I have informed earlier, which stands for unitary group in n dimension. Because H is a Hermitian, this H is a Hermitian, naturally the diagonal matrix elements are real because those elements are indicating the eigenvalues. Since a trace of a Hermitian matrix is equal to alpha, uh, the alpha must be real because the trace of the Hermitian matrix must be real. So alpha must be a real quantity. Then determinant of u can be u is equal to determinant of e power I h. Using this definition, determinant of u is equal to e power I h. Uh, then which is equal to e power e power I trace h. This can be written as determinant of e power I h is nothing but e power I trace h. We know the trace h is equal to alpha, so e power I alpha. Uh, so the determinant of u is equal to e power I alpha. That is a phase factor. If alpha is equal to 0, then naturally this determinant of u is 1. So not the modulus of determinant is 1. Just determinant of U unitary matrix is 1, provided alpha is equal to 0. That means trace of the Hamiltonian matrices is 0. So that is a traceless matrix. We will see some detail about this within couple of minutes. Right now, you remember that if trace of the matrices is equal to 0, then the determinant of the unitary matrix is equal to 1. That is a very important point. You have to keep it in your mind. Thus, if the determinant of U is required to be equal to plus 1, a single constraint is placed on n squared parameter. See, if it is n by n square matrix, uh, if n is equal to 3, you have 9 parameters. However, we are imposing a condition alpha is equal to 0. That is, trace of the matrix is 0. That means if it is a 3 by 3 matrix, only two entries in the diagonal element can be varied. That element is not an independent one. That depends on the first two diagonal element. We will see it later about this alpha is equal to 0. That is a traceless matrix. These matrices also form a continuously connected compact Lie group. It is designated SUN, that is special unitary matrix N, has n squared minus 1 parameter because there is one constraint. It's traceless. Every member of SUN is clearly member of UN, but converse is not true. That is, SUN is therefore said to be subgroup of UN. The UN, in the case of UN, uh, it is clear that the modulus of determinant of UN is equal to 1, whereas in SU matrices, it is uh, plus 1 with the condition that it is traceless. So you cannot fix a third element in the diagonal entry. Only two you can fix. The third one is depends on the other two element. If it is 3 by 3 matrix, we will see it now. Obviously, both UN and SUN are the subgroup of a unitary matrix M if n is equal to or less than m. This point we will concentrate within couple of minutes. Now we will see some of the general properties of special unitary group. SUN is a compact Lie group. They are unitary, finite dimensional, and irreducible representation. The unitary group has n squared parameter, that is its dimension. If it is n by n matrix, say let us say it's 3 by 3 matrix, it has a 9 parameter and it rank has n minus 1. Here n is equal to 3, so 3 minus 1, 2. And this rank indicate its number of Casimir operators. We are going to see it in detail. The Bessel unitary group has n squared minus 1 free parameter because one parameter you cannot fix. You can fix the 8 other parameter. That also we are going to see it. That is its dimension. Its dimension is not n squared. It is n squared minus 1. For unitary group, the dimension is n squared. For Bessel unitary group, it is n squared minus 1. And it has a rank n minus 1. That is its number of uh, Casimir operators. Now we will see the generators of SE2 matrix. In the case of n is equal to 2, the Bessel unitary matrix group unitary group has n squared minus 1, that is 2 squared minus 1, 3 parameters. A convenient choice for these three generators are naturally the poly spin matrices, which is a 2 by 2 matrix. Here you can fix three element. One of the element you cannot fix because take the example sigma Z matrix. Since it is one, the other diagonal element must be minus 1. It is not under your hand because it trace must be equal to 0, traceless element. So you can fix only three element here. So number of independent entries are only three. Fourth one is fixed by other element. So this is about the polyspin matrix. According to the theorem of Rakak, the number of independent operators that can be constructed from the generators like J squared or S squared or L squared. I have explained already this. All these operators are comes under Lie group. Whatever property is valid for J squared is equally valid for L squared or S squared. Here, this will commute with poly matrices S squared, which is equal to Sx squared plus Sy squared plus Nz squared. So, uh, these are the S squared commute with Si squared, where I is equal to XYZ. That commute with all generators of Lie group. Here generator are Sx, Sy and Sz matrix. And it is equal to the rank of the group. It was first recognized by Casimir that one such operator can always be formed by taking a suitable bilinear combination of the generators. I told the example just now, that is L squared is equal to linear combination of Lx squared, Ly squared plus Lz squared. Similarly, similarly, yes. So they are therefore called Casimir operators. Since SU2 is of rank 1, here rank is n minus 1. Hey, n is equal to 2, so 2 minus 1, 1, rank is 1. It is only Casimir operator is, it's only a Casimir operator is, in this case, we can take S squared. I have written here J squared. Here only Casimir operator is S squared. So because S squared also comes under Lie group. I have taken J as a general form because it's contain this. This is the total angular momentum L plus S, orbital angular momentum plus spin angular momentum. Now we will see about SU3 groups. The Basel unitary group in three dimension has 3 squared minus 1, that is n squared minus 1, which is equal to 8 generators. Those generators are labeled as lambda 1, lambda 2, lambda 3. It will go up to lambda 8, which may be chosen in the many convenient way. Since SU2 is useful subgroup of SU3, we specify those three generators, generators of SU3. That is, we can use the polyspin matrices as a generator of SU3 also, because SU2 is a subgroup of SU3. Now we will see that this is sigma x. We are introducing an additional row and column with zero element, zero entry, 0, 0. So this sigma x here, third row is 0, third column also 0. We are adding zeros. So this will not change the determinant. So this is we are calling as lambda 1. Then lambda 2 is 1. Here you have the sigma matrix, polyspin matrix, and third column we are introduced to 0. third row we have introduced to 0. Similarly, sigma z we have written as lambda z using the entries third row as 0, third column as 0. So it has all the property that this polyspin matrix has. So these three elements are the polyspin matrices. We will see other five matrices. The, uh, these first three of the lambdas evidently satisfy the same commutation relation of sigmas, that is polyspin matrix. The relations may be written as commutation of sigma I with sigma j is equal to 2I summation over k epsilon ijk sigma k. Epsilon ijk has its usual meaning. So we have find three lambdas. We have to find five more lambdas that we will see. The remaining five lambdas may be still be chosen in many ways. However, since the principal of applications of SU3 algebra is to the classification of elementary particle, we follows the notation adopted in that connection because we are applying to the elementary particle. So we are adopting some standard technique. These lambda matrices are called Gell-Mann matrices. Already we have seen lambda 1, lambda 2, lambda 3 is subgroup of SU2 matrix, that is polyspin matrix. First four elements, these four elements are polyspin matrices. Just now we have seen. Now you can see, you can compare lambda 1 and lambda 4. See, we have shifted, we have made this second column and second row as zero element. We can we can construct these lambda matrices in so many ways, but this is because we are dealing with elementary particle, we have formed in a particular way. You can easily understood the polymatrices is sigma x is equal to 0, 1, 1, 0. Here, second row, second column, we made it 0. Similarly, here, second row, second column, we made it 0 in. So this is 0 I 0. So similarly, the lambda 6, you can see here we have made first row and first column as 0 entry. So this will be uh, what one? Sorry, this is the 0 1 1 0. This matrix, sigma x matrix, 0 1 0 1 0. So we made it first row and first column as a 0 element. Here also you can see lambda 7 is equal to this I. You can compare this. I 0 I I0, 0 I0. We made it first row and first column as a 0 entry, and sigma 8, sorry, lambda 8. Lambda 8 is a, diagonal element, diagonal matrix. So first two elements are fixed, 1, 1. So naturally the third one must be minus 2. This is what I have told as a constraint. This element, fixing this element is not in your hand. You cannot independently fix this. It depends on the other two diagonal element. This is minus 2, lambda 8. So basically, we have this is the unit matrix that is first two. 1 0 0 1 is a unit matrix. Here it traces this diagonal element is minus 2. See, we have constructed this using polyspin matrices. Uh, or if J is equal to 1, we have 2, M is equal to that is magnetic quantum number is equal to 2J plus 1. So J is equal to 1, you will have 3 by 3 matrix in which 8 elements are independent, one is dependent on these two. So, similarly, the commutation relation is equal to that of polyspin matrices. That is lambda I, commutation of lambda I with lambda j is equal to 2I Fij lambda k. Here, Fijk is called Truxer factor. Uh, and this is see, if it is fermion, we know elementary particle, it is antisymmetry. That is the commutation relation is lambda 1 lambda 2 minus lambda 2 lambda 1. That is, you are interchanging the particle, so it is antisymmetric structure factor, and it is defined as Fijk is equal to 1 over 4 pi 4i trace of the commutation of lambda I with lambda j multiplied by lambda k. Similarly, uh, trace of lambda I lambda j is equal to 2 delta ij. This is Kronecker delta. So you know the meaning of this. Similarly, this is Tijk also Truxer factor. In the case of fermion, that is polyspin matrices, this coefficient must be equal to 0 because that is related to fermion. It is anti-symmetry. Whereas Tijk is a Truxer factor due to symmetric Truxer. So this is a symmetric coefficient, which is equal to 1 over 4 trace sigma I, commutation of lambda I with lambda j. Uh, See here, I have used a plus symbol. It is anti-commutation. Anti-commutation means lambda 1, lambda 2 plus lambda 2, lambda 1. When you will write like this, only uh, if the particle is having symmetry, that we have in the we have seen it in the uh, identical particle. So if it is symmetry, you will get plus instead of minus, you will get plus. So it is anti-commutation relation. So this coefficient Tijk is equal to 1 over 4 trace commutation of lambda j with lambda I with lambda j anti-commutation. In fact, sorry, anti-commutation of lambda I with lambda j multiplied by lambda k. Here, here we have seen n equal to 3. When n equal to 3, how many Casimir operator we will have? That is n minus 1. Since n is equal to 3, we will have two Casimir operator. That is 3 minus 1, two Casimir operator. One operator we are naming as C1, which is a function of lambda I is equal to summation over 1 to 8 lambda I squared. See, you remember that the in the case of orbital angular momentum, this is Li squared is that is L1 squared, L2 squared, L3 squared. Similarly, J1 squared, J2 squared, J3 squared. If you add all the square of the angular momentum operator or total angular momentum operator or spin operator, that will commit with the individual operator of the spin or angular momentum or total angular momentum. J squared will commit with Ji, that is where I is equal to XYZ. So same thing is true for this case also. We are squaring all the matrix and adding, summing up all the 8 matrix. So naturally, this will commit with the individual matrix of lambda I, where I is equal to 1 to 8. So this is one operator. Then another operator. This is a symmetric operator, that is summation over ijk. This operator is C2, which is a function of lambda I is equal to summation over ijk, Tijk, lambda I, lambda j, lambda k. So now, if you take ijk as one row and fijk, here 1, 2, 3 refer the ijk value. Similarly, 1, 4, 7 also ijk. Then corresponding fijk is 1. Here it is half, minus half, 1, half, half, minus half, it will go like. So you can construct the table like this by using these two relation. Tijk, sorry, previously I defined this relation. So uh, you have 9 such element for Fijk. Similarly, for Tijk, you have 16 element, 16, 366, 377, it will go like this. Um, so you can see here, if you carefully watch this number, here no integer is repeated. Same 1, 2, 3, 1, 4, 7, 1, 5, 6, 2, 4, 6, 2, 5, 7. So no two numbers are equal, uh, because it's a anti-symmetric. If any two number is equal, then it will become naturally zero. Here you can have same number 118. You can see 228, something like 44. So because it's a symmetry in nature, you are adding. So this is about the structural coefficient for the Gell-Mann matrices. Uh, Thank you very much for watching my videos and supporting me continuously. If you have any question, send to the following mail ID, vasimku@gmail.com. My YouTube channel ID is youtube.com /at vasubp6. Thank you very much.